All right, let's get started then.
Okay, so for those of you who I haven't met yet, hi, I'm Josh Whitley. I'm an independent autonomy software engineer under the business name Whitley Software Services. I work for a handful of clients in around the world and primarily in Silicon Valley. I work on everything from automation of flight control systems all the way to autonomous ground vehicles, which is mostly what we're focusing on today. And prior to this, I worked for the Autoware Foundation as their system architect, who developed Autoware.auto and previously Autoware.ai. And then before that, I worked for Autonomous Stuff, which is a sensor distributor and systems integrator that does a lot of the autonomous ground platforms for the companies that are researching autonomous vehicles. So I think mostly today we're going to be going over what we had you guys install on your laptops or PCs. Just to verify, everybody that's in this call, do you have a machine available to you where you're sitting right now with Ubuntu 20.04 and ROS2 Foxy installed on it? Does anybody not have that? If you could. Okay, looks like everybody that's got video on is good. And if anybody has any issues as they kind of go through this stuff, then please feel free to raise your hand in Zoom or put a message in chat. I'll try and keep an eye on those. So I think the first thing I would like everyone to go through is a couple of the basic tutorials in the ROS2 documentation. And the reason for that is not because I'm lazy and want to use someone else's stuff, but because they actually have really good tutorials that help you learn the basics of ROS2 and get an understanding of how ROS works as an architecture through a couple of just little simple introductions of how to run some commands on the command line, how to get some nodes up and running in ROS, and then basically like run around a little image of a turtle to get things started. So I'm going to share my screen real quick, and then I will paste a link to the tutorial. This one. Here we go. So I've also opened up some other images here, and I will make things bigger because I know my screen is huge and it's really hard to read. So does that look okay for everybody? Okay, cool. Thank you. All right, so you should have already gone through the installation section. The docs guide is not super useful for people who are new to ROS. In general, it mostly talks about the differences between ROS1 and ROS2 and documents the infrastructure a little bit. And I'll go through the infrastructure kind of later in this call, once you've had a little bit of hands-on experience with working with ROS2 and running some things inside of it. So the first thing we're going to go through is the tutorials. And I'm actually going to change which version of the tutorials we're looking at here, because just so you're aware, there are quite a few different distributions of ROS that are available. Right now, the most recent ones for ROS2 are Foxy Fitzroy and Galactic Gale Shalom. These names I know all look really weird, but they're actually an adjective followed by a species of turtle, just in case anybody is curious where these weird names come from. And then there's also a version that's not mentioned on here, which is Rolling Ridley. And Rolling Ridley is a rolling distribution, which means that as changes are made to parts of ROS2, they automatically get added to rolling. And anytime a new official distribution is made, like Foxy or Galactic, they actually cut a version of rolling and say, this is how we're going to release it for this new distribution. And then from then on, maintainers of packages within ROS need to maintain their most up-to-date version, which goes into rolling, and then the released version, which will go into the release that was cut at that point in time. And you can also see some of the information here about their support dates. So Galactic, for example, is not a long-term support release. Therefore, it'll only be supported from May 23rd, 2021 to November 2022. So it's an 18-month support period for non-long-term releases. And normally it's a 5-year support period for long-term releases. but Foxy was kind of an exception because ROS2 was still fairly new, and not all of the base functionality that they wanted in ROS was available at the time that Foxy was cut. So they're only supporting Foxy until May of 2023, but that's the longest term, long-term release that we currently have available. So that's what Autoware is currently running on. So going back to the tutorials we were talking about, the first thing we're going to go through is some basic configuration of your ROS2 environment. So everybody go ahead and open up a terminal on your Ubuntu machine with ROS2 installed. So the first thing we're going to talk about is workspaces. So ROS kind of runs on the idea of workspaces, and even all of the stuff that you installed as part of the ROS2 Foxy desktop package, that was all installed in a workspace on your machine. And that workspace lies under the folder opt ROS Foxy. So the setup.bash file gets generated for every workspace that you create on a ROS2 machine. And this setup file basically tells your bash environment, here are where all the important files are for ROS. And if you're looking for a specific file to launch or a node to run, these are the folders that you should look in when you try to do that. So the first thing you want to do in your terminal before you run any other ROS commands, since we don't have another ROS workspace set up, is we want to do what's called sourcing the workspace, which is running this command right here, source opt ROS Foxy setup.bash. And I said that I was going to paste this link in chat, and I haven't done it yet, so let me do that now. So feel free to follow along in a browser as we go through this if you want to. So once you've run that command, you're essentially loading some environmental variables and other things into your bash environment. Now, to make it a little bit easier so that you don't have to run this command every time you start up a terminal, you can add it to what's called your bash RC file, which is your environmental setup script that's in your home folder. And running this command, the echo source opt ROS Foxy setup bash, right bracket, tilde / dot bash RC, this says take the text that I've got here in the echo command and put it at the end of this bash RC file. And every time you open a new terminal, this bash RC command bash RC file gets run, and anything that's inside of it gets run. So this will make sure that every new terminal you open automatically does this, and you don't have to do it for yourself. And then just to get an idea of what this script is actually doing, you can run this command if you want to. This is totally optional, but this will print out all of the environmental variables that are getting set by the source command that you ran up top. So most of them start with or contain ROS. So this is just saying print all the environmental variables, and then grep, which is kind of like a text filtering program, look for the term ROS and print out any environmental variables that contain ROS. So you should see a few of them in there, things like ROS version, which was only introduced with the advent of ROS2. So it will let the system know whether you're running ROS 1 or 2, which version of Python ROS is using, and then which specific distribution you are running on your system. We won't get too much into the ROS domain ID variable. You basically just need to know that this is the way that you would segment traffic on a network that has multiple instances of ROS on it. So it's basically just a unique ID that you tell ROS, hey, you're running under this ROS ID, and all traffic you transmit is going to be under this ROS ID, so that if you have another ROS instance running on the same network, they won't cross over. All right. Now we're going to get into a little bit more of the running nodes and actually playing around with some stuff in ROS. So we're going to go to the turtle sim demonstration. So in order to actually run the turtle sim nodes, we do have to install some packages. And the major point here is that there are really two ways to run ROS packages. You can either install them from binaries that are available on the ROS repository, which is what this apt command is doing, or you can download them from source from places like GitHub or GitLab, and then in your ROS workspace, you can build them and then run them from that workspace. But for now, since we're just going to be running some example nodes that are already written, already available on the ROS build farm, you can just run these two commands, sudo apt update, which will take about 15 seconds and make sure that all of your package references are up to date, and then sudo apt install ROS Foxy Turtle Sim. And that will install a copy of the Turtle Sim package and also all dependencies that are part of that package. All right. And also, just as an FYI, if anybody goes through one of these commands and they get stuck, have a problem where they're not able to proceed, please raise your hand or open up your mic and let me know. Otherwise, I'm just going to kind of continue rolling and assume that everybody's commands are running okay on the terminal.
Just a quick poll, how many of y'all have ROS installed? Okay. And Shuman, what about you?
I'm sorry?
Do you have ROS installed?
Yeah, ROS2.
Okay, okay. So
Cool.
is there anyone who, besides Jeff, who does not have ROS installed? Okay, so it looks like they're all covered in with ROS.
Cool.
Okay.
Good to hear. Okay, and then once you install the Turtle Sim package, you can check to see that the package exists and that it has nodes or executables associated with it by running the command ROS2 pkg executables Turtle Sim. And essentially, this is where we actually start to get into the ROS2 commands that you will work with pretty regularly for getting around your ROS2 environment and running and launching things from within packages. So the ROS2 command is the verb that you start all ROS2 commands with. This differentiates it from ROS1. ROS1 actually had a lot of commands that were things like ROSRun or ROSLaunch. And now all of those, when they came into ROS2, have become ROS2 space and then the command that you want to run. So ROS2 package executables Turtle Sim will list all of the nodes or executables that are part of the Turtle Sim package. So you should see these. They may have added a couple of more since then, so don't worry if you've got a couple extras there. But the ones that we really care about are things like Turtle Teleop and Turtle Sim Node. So the first one that we're going to run, just to make sure that your system is running, that ROS2 knows where to find everything, and that it can open a window for visualization, is ROS2 run Turtle Sim Node. And the format of this is pretty important. So keep in mind, most commands that you run are going to be ROS2, some verb that you want to do something with, like run or launch or package, and then the name of the package that you want to look inside of, followed by the node or script or executable or whatever that you want to execute within that package. Did anybody that's on the call do an install either in a virtual machine or in a Docker environment? Okay. Doesn't sound like it, but just in case, if you are using a virtual machine, you're probably going to be okay with running this. If you're using a Docker environment, this actually may not come up because in Docker, by default, it doesn't allow GUI applications to run on your host machine. So this would probably fail with a couple of like errors about GTK, but I think we're okay. So when this window comes up in the terminal, you should see a couple of messages from the node itself, just giving you some information, starting Turtle Sim with the node name Turtle Sim, and then it's spawning a turtle at some coordinates that are on the screen. Does anybody have anything different from this or see any problems with launching this application? Okay, sounds good. So another thing that you'll be doing a lot of in ROS environments is launching multiple terminal windows. So you can either create a new terminal window that's completely separate from the one that you already had, or in a lot of cases, if you use the default Ubuntu install, you'll get your terminal that you're running is called GNOME terminal. And in that terminal, you can create a new tab in it instead of creating a whole new window by either going to tabs, new tab, or you can do Control-Shift-T if you're a keyboard person like me. And that will open a new tab. And then in that new tab, you can run ROS2 run turtlesim teleop, or excuse me, turtle teleop key. And this node allows you to essentially drive the turtle around in the window, in the visualization window using your keyboard or the arrow keys on your keyboard. Does everybody see that? Is it working okay? Cool. Shimon looks good.
I'm getting command not found on my laptop.
Okay. When you get command not found, is that in the new terminal that you created?
Yeah, it's a new tab I created.
When we were doing the setup for the workspace, did you do the command with echo and then it was going out to the bash RC file?
I'm sorry?
So in the configuring your ROS2 environment part earlier in the run through, did you run this command right here? Echo source optrock bash RC?
I'm not sure. Yeah, I think I did. Yeah.
Okay, you can find out if you just type the word tail, T-A-I-L, and then space tilde slash dot bash RC. And essentially what that will do is it will print out the last few lines of this file, the dot bash RC. And if the last line shows source ops ROS foxy setup.bash, then it means that you ran that command correctly earlier. If not, then you can just run this command in your terminal.
Yeah, it shows some if else statements, and in the end it's conda initialize.
Okay, so it's missing this source op ROS foxy then at the end.
Yeah, probably.
Okay, so if you run this command in your terminal, and then you close that terminal and open a new one, that other command for the turtlesim teleop key should work now. And the alternative to that is when you open a new terminal, you can manually source optros foxy setup.bash, and that will essentially do the same thing.
Yeah, it works now.
Okay, cool.
Thank you.
No problem. Okay, so now we're just going to go through a couple of common ROS2 commands. So when you are working with or troubleshooting a ROS2 system, these are going to be some of the most useful commands to figure out what's going on in the environment that you're looking at. Because once you start running a large number of nodes and you have complex pipelines for things like perception processing, planning, those sorts of things, you're going to get a node graph of how all the nodes are connected that's very large and complex. So these commands are really important to help you learn what is running on the current ROS system, what nodes are connected to which parts of the environment, and so on. So again, in a new terminal, I would recommend opening another one and then just typing ROS2 node list. And in that new terminal, you should see, I believe, only 2 nodes running at this point. Real quick, I'm going to go ahead and stop sharing, and I'm going to just briefly do a couple of pieces of setup. So I recommend running all of these 4 commands here while I'm doing that. So ROS2 node list, ROS2 topic list, which we'll get a little more in detail into what exactly topics are and how they communicate in ROS in a few minutes. ROS2 service list, and ROS2 action list. Again, the services and actions we probably won't get too deep into today. I would say topics and services and nodes are probably the 3 main concepts that you're going to run into most often in ROS2. So give me just a second on the setup. All right. I'm going to start sharing my screen again. Oh, and let me turn off opacity because you guys probably won't be able to see that very well. Just in case we do want to run into any issues, I just want to make sure I've got the same layout that everybody else has. Oh, whoops. Okay. All right. So yeah, we've got the two ROS2 nodes running here, TeleOpTurtle and TurtleOpSim, and then ROS2 topic list will show you any of the topics that are currently being used. If you are running no nodes at all, you will still see the ROS out and parameter events topics. Excuse me, those are kind of what you'd consider system topics. ROS out is where all logging commands are sent from all nodes that are running on the ROS system. And then parameter events is a generic topic that's used to report when changes are made to parameters dynamically on nodes that are running on the system. Everything else that's under what we call a namespace, so /turtle1, is a topic that's being published or subscribed to on one of the two turtle nodes that you're currently running. Spawn service. Okay. So the next step is going to be installing RQT, and RQT is kind of a framework for plugins and visual GUI applications within ROS. So you probably don't need to run sudo apt update again because we just did it recently for one of the older commands. But you can run sudo apt install tilde nros-foxy-rqt star. And this is kind of using some regex stuff to select a certain subset of packages. But that will install all of the RQT commands that you care about within your ROS environment. So you'll get, I think, 33 newly installed packages as part of that. And that should be fine. And then you're going to use RQT itself. So you just need to run RQT, and it will open up a window. Now it's going to look like this window is blank and doesn't have anything in it. And that's because RQT itself is just kind of the plugin architecture. RQT does not have any functionality other than being a space to drop plugins in. So in order to add some functionality to this window, you're going to go to plugins. And then in this case, they want you to add the service caller function. So go to plugins, services, service caller.
It's a bit tiny.
Yeah, sorry about that. Let me see if I can increase it on here. Yeah, unfortunately, I don't have the ability to make the text any larger on this one, but on your machine, it should be a little easier to read, I hope.
Yeah, I can move closer.
Cool. Okay, so they want you to make sure that all of the services are available in this drop-down box. So if you have, if you click the drop-down box next to the word service and you don't see a bunch of options in here, then you should be able to hit the button just to the left of the word service, which in my case is missing the little refresh icon, but in yours it may have it. And that should refresh the list of services that are available in the drop-down box. So what we want to do is use the spawn service, which is going to spawn another turtle. So drop the box down for service and choose spawn.
Sorry, I kind of missed the first step. How did you bring all those things up?
So do you have the RQT window open?
Yeah, yes.
Okay, go to plugins, services, service caller.
All right. Okay.
Cool.
And
then drop the service box down and choose /spawn.
All right. I don't have the spawn one.
Yeah, try hitting the button just to the left of the word service, which should refresh the service list. And then see if the drop-down box has it in it now.
No, I have RQT GUI Pine node and then /describe parameters.
Okay, so do you still have your turtle teleop node running? And your turtle node?
I closed them.
Okay. That would cause those to go away. Yeah,
okay.
So go back into those terminals and just run those nodes again, and that will add the list of services back.
All right.
So that's something worth noting as well, is that services are tied to specific nodes. So when you create a service, you are saying in the code, you say this node will have this service attached to it. So even though the service that you're looking at here is /spawn, it's actually attached to the turtle sim node that's running in the service. And if you don't have it available, it's because that node is not running.
Got it. Okay, now I have the spawn.
Okay. Anybody else up to this point have any issues with the service caller application? Okay. All right. So moving on in the service caller application. So under the request box, you'll see a set of properties and the expressions that are filled in for them. So what you're seeing here is actually the content of the request that you're going to send on this service. So you'll see X, Y, theta, and a name. And those are the properties that you're going to actually be sending via text to that service to tell it what to do. So in order to give a unique name for the turtle that we're going to add to the turtle sim node, you need to type in the expression box for the name property. So double click in that box and you should be able to type a value in there. Just use something like turtle2. And then just for the heck of it, we can add a new starting position. So for the Y property, put in the expression 1.0. And for the X property, do the same thing, 1.0. And you may have to hit Enter or Tab to leave the expression box. And then once you've filled in those properties, just click the call button next to the service dropdown, and it will call that service. And then you should see a response pop up in the bottom of the service caller window. So in this case, the definition of the service basically just returns the string name of the new turtle that you spawned. But if you switch back to your turtle sim application, you should now see a new turtle show up in the window. And then if you also go back to your window that's running the turtle teleop and try to move the turtle around, you'll notice that you're still driving just the one turtle. And the new one doesn't have any teleop functions connected to it. And we'll get into how that works later and why it's only driving one of them. But I will say it has a lot to do with topics. And then in the RQT service caller, if you now refresh the list of services with the button on the left, you should see some additional services that have popped up. There were previous ones associated with Turtle 1, with the namespace Turtle 1, and now there should be some Turtle 2 ones as well. So what we're going to do next is to basically change the color of the drawing pen that's being used for the first turtle. And that's also available as a service on the TurtleSim node. So in the service caller, drop that box down and change to Turtle1 set pen. And then this is being defined with an RG and B color value, a width, and then whether you want to turn the pen on or off. So the RG and B values are going to be between 0 and 255. You can set them to whatever value you like. And theoretically, if you set them to a value outside of that range of 0 to 255, it should not let you set that value because the type of uint8 only goes to a value of 255. So when I try and set a value to 256, I get a response back, but there's nothing in it. And that means that the service failed to be called properly. I believe that's the case on this one anyway. Actually, no, it looks like it takes it anyway, even with an invalid value. So. All right, so change these as you'd like and then hit the call button. And then when you go back to your turtle window with your turtle teleop node, when you drive it around, the turtle's drawing color should change, as well as the width and the on-off function. Okay. Now we're going to get into a little bit more about topics. So what you've been doing so far is calling services, and services are really for one-time changes or property values that you want to change on a node that don't need to be constantly updated. Whereas topics are much more for passing information back and forth between nodes and publishing data that needs to be constantly updated, like sensor information or position information. So what we're going to do now is we're essentially going to run another instance of TurtleSim, but we're going to remap one of the topics so that we can control Turtle 2. So if you open another terminal and then use this command, ROS2 run TurtleSim turtle teleop key, and then you have to pass it some arguments for which topics you want to remap, then this node will connect together two of the topics which are currently not connected. And when you open this window and run that command, if you keep that window open as well as your TurtleSim window, the keyboard in that TurtleSim window should now control Turtle 2. So essentially what you've done in this remapping is you've said in the node that I'm launching, which is turtle teleop key, take the topic, which is currently named turtle1 command vel or command velocity, and remap that so when this node launches, it is instead launching it with the name turtle2 command velocity. And since the teleop node is the one that takes your keyboard commands and turns them into velocity commands for the turtle, you're now controlling turtle2 in this window instead of turtle1. Okay.
Hi, Josh.
Yeah.
In that command, when you press like either the G, T, or R, which is an absolute rotation orientation, it still rotates turtle1.
Oh, yes, actually, that's a good point. So there are two topics that are controlling each of these turtles. There's a command velocity, and then,
okay.
Just a second. So there's a command velocity and a pose. And
Okay.
the command velocity only controls the forward velocity of the turtle. The pose controls the position of the turtle.
Okay, got it. Yeah. Thank you.
Mm-hmm. And actually, we can. This is a good point and a good place where we've got a couple of nodes started and some things that we can learn from this setup that they don't really go through in the tutorials, which I think are pretty important. So ROS2 topic list has a couple of parameters to it that you can add, which will help you identify what messages are being passed, and in some cases, what nodes are publishing to and subscribing each of those topics. So if you run ROS2 topic list -t, you will get the list of topics and also the type of message that's being sent on each of those topics. Many of these you'll see start with TurtleSim, and that's because those messages are defined within the TurtleSim package. And you can actually get a description. For example, if you want to see what is part of this color message, you can run ROS2 interface show, and then the full name of the message type that you want it to describe. So let's use the color message. And this will give you the full contents of the definition of that message, which in this case is just 3 uint8 values for R, G, and B. Pretty simple one. But there are significantly more complex messages. Twist gets a little more complicated. So geometry messages is actually a standard ROS package that includes a lot of common things that you need in robotic environments. Things like twist, which allows you to control the position and orientation, or excuse me, the acceleration and velocity of an object. Pose, which allows you to control the position and orientation. Let's see, other geometry messages. Point, twist, odometry is another one that combines orientation and position. So there are a handful of them, and you'll find a lot of useful geometry messages in there that you use in a lot of projects. So we'll also look at the geometry messages twist. And you can see here that they have an linear and angular velocities. And those are of a type called vector3. Now, because this doesn't have any prefix on it, we know that vector3 is also in the geometry messages package. So you can look at the content of vector3 as well. And you can see that that is broken down into an X, Y, and Z. And in the case of linear, it would be the linear X, Y, and Z velocity, and angular would be the angular X, Y, and Z velocity. So a lot of these messages are stacked this way, where you have a definition that is broken up into other message definitions. I think. Okay, never mind. So the other thing that I was talking about with ROS2 topic is you can also show the connections that are happening on an individual topic. So for example, the one we were talking about before was turtle1 command vel. So to find out who is publishing and who is subscribing to turtle1 command vel, you can run ROS2 topic show, and then the name of the topic that you want to see the details on. Or sorry, not show, info, my bad. turtle1 cmd vel. So without any other parameters on ROS2 topic info, you will just get the type of message that's being published there and the number of publishers and subscribers. However, if you do ROS2 topic info, the name of the topic -v for verbose, you will get complete information on the individual publishers and subscribers that are being publishing to and subscribing to that topic. So in this case, for the publishers, we have the teleop turtle node. That node is running in what's called the root namespace, which is just /. This is the type of message that it's publishing. The endpoint type is publisher. And then we won't get too deep into the QoS settings, but basically know that these are how you control how often a message is republished, what to do when a message gets dropped, whether this should be higher priority than other message types, etc. All right. So you can go ahead and shut down all of the nodes and other services that we've been running. And you can do that just by, in each of those terminals, do Control-C, and that will stop the node. And then if you want to close any of those terminals, once you have nothing running in the terminal, you can click the X on that tab to close the terminal, or in the terminal itself, you can just type exit, and that will close out that terminal window. You'll see me doing it twice in a couple of places because I'm actually running a containerized Docker environment, and I have to exit from that and then exit from the terminal window as well. Okay. So the next one that we're going to talk about is how ROS2 nodes work and how they connect to each other. So if you are on the TurtleSim tutorial, click on the Understanding ROS2 Nodes link at the very bottom. So this page gives a fairly simple animation of how ROS2 nodes are connected to each other. You saw a lot of this in the TurtleSim example, but this goes into a little bit more detail about how a single publishing node can publish to a topic which can be subscribed to by multiple other nodes. So it's a one-to-many relationship for publishing and subscribing. Now, theoretically, you can have multiple nodes publishing to a single topic. That is pretty rare. There are definitely some corner cases where it's really useful, but it's not that often that you will have something publishing information and you also want another node to publish on the same topic for the same type of information. In the case of things like ROS logging, where all nodes are publishing to the ROS out topic, that case you want all nodes on the system to be publishing to a single topic because you want to be able to conglomerate all of the logging information across the system. And there are cases where, for example, you want, like if you want to take multiple inputs from a couple of different joysticks, for example, you can have both of those joystick nodes published to the same topic and then have one node listen to that and listen to whichever one happens to be publishing data at that time. You do want to have either some physical or some software-based controls to make sure that you're not publishing different messages from different sources at the same time, but there are use cases for it. And then the services that we were using are set up in this configuration where a node is talking directly to another node through a service. One of those nodes has a server on it, which is the one that receives service requests and then will respond with a service response to another node that has a service client running on it. And we'll kind of see a C++ example on how that works. All right, so we've been going for about 45 minutes here. At this point, we're kind of halfway through the time that we had allotted. So real quick, I just kind of want to open it up, see if anybody has any specific questions that they'd like to know about ROS2 in general, about the tutorials we've been looking over, or any of the commands we've run. Okay, pretty quiet. Gonna assume everybody understands everything completely at this point, and you'll be able to pass a test at the end of this, right? All right. Do we want to take like a short 5-minute break, or do we want to just keep rolling?
You can go on.
Okay. Sounds good. So I'm going to jump into kind of a little bit more high-level concept stuff about how ROS2 works from an architectural level, and how you actually write applications that run on ROS2 and how they interact with the lower levels of ROS2. So the ROS2 architecture is set up like this diagram, where user applications are the nodes that we've been running. So the TurtleSim node, the teleop node, all of those were written in C++ or Python, and they all interact with lower levels through what's called an RCL. RCL stands for ROS Client Library, and that is the API interface for a specific language to talk to the rest of ROS. So the two primary ones that you'll see mentioned most often are RCL CPP, which is the C++ API for ROS, and RCL Pi, which is the Python API for ROS. In previous versions of ROS, like in ROS1, these were completely separate binaries that would interact with ROS in their own ways. And because of that, you had little quirks here and there where you get specific functionality that would only work in one language or another when you were communicating with ROS. But in ROS2, that's been completely rewritten so that there is a common RCL written in C, and then all other languages use an interface layer to talk with that C API to do all of the basic functions. So the RCL CPP layer is a C++ wrapper that calls functions that are in the C API down at the core RCL layer. And the Python essentially works the same way, but it's using C bindings to talk to the C API. But you're calling all the same functions from that other language. And that's why you can write pretty much any language-specific RCL you want. Like they have a Java API. These are the only 3 that are officially supported by the Open Robotics, which is the organization that kind of stewards ROS. But there are plenty of other ones that are available through community support. So there's a Node.js, RCL Node.js, there's a C# one, there's a Rust one. So whatever language you want to write in, it's usually possible to write those applications on top of ROS. However, since C++ is the primary language that's supported by Open Robotics, and since C++ is more efficient and more type safe than Python, most applications for autonomous vehicles will be written in C++ on the RCL CPP API. Below the RCL C API, where all of the basic functionality is implemented, you get what's called the RMW. And the RMW stands for ROS Middleware Layer. When you are sending a message to a topic, you will have a user application that says, I want to publish a message to this topic name. That call will be made inside your specific RCL. So in the C++ API, it would be topic.publish. And then you would give a copy of that message to the publish function, which would send it down through the RCL, where it's the common functionality for all languages. And then that would get passed to the RMW C API. And then that gets passed to a DDS implementation. DDS is an industry standard for a message communication system. DDS is an open standard you can find on the web. The DDS protocol is managed by a standards organization. So every DDS message has to have the same structure to it. The way that messages get passed between nodes, the ways that services are represented, all of those have to be identical because they conform to the DDS standard. But there are different companies that implement different functionality on top of DDS. So you'll see implementations like FastRTPS, which is now actually called FastDDI or DDS, RTI Connect, and they make an implementation called Connects to DDS. There's another one, which is the one that I'm using and the one that I think is most popular in open source, which is called Cyclone DDS. And that's an open source initiative by another company. So regardless of which DDS implementation you use, the RMW layer in ROS kind of smooths over all of those differences between the DDS implementations. The RMW is really the only thing that your applications above that have to care about, because it's a common set of functions that on the surface always have the same functionality, and then how the DDS vendors implement them is really up to them. But the RMW layer stays the same for every DDS implementation. Yeah, so this gets a little bit more into how specific message types and IDL files and so on get implemented in the RMW. I think that's probably a little beyond the scope of what we're talking about here. This architectural document, which is about the internal interfaces, I'll go ahead and put this link in chat if any of you are interested in digging deeper into it and really want to punish yourselves. But it gets really far into the weeds about how types are implemented and how the types are dynamically use type polymorphism to represent them in the RMW, blah, 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 blah. It gets really deep, but just in case you're interested, there's a link to it. So some of the stuff that we will go into, the ROS2, let's see. Let's start with parameters. Parameters you're going to see pretty much everywhere in all ROS nodes. Parameters are a way to be able to configure a node on startup and then change the values of those parameters at runtime. So you can hard code them into your node and say, I want this parameter to start up with this value. But then when you launch the node, you can pass in parameters and say, I want to change this parameter value on startup to be something else. And that allows your nodes to be much more dynamic and be able to do things like run a driver for a sensor and be able to pass in the IP address of that driver as a parameter, so that you don't have to have that hard coded into the node, and there's no way to change it except changing the code and recompiling everything. So there are a handful of parameter types that you can use. Most of them are bound to basic C, C++, Python, etc. Types. So you can do things like Booleans, integers, doubles, and strings. And that's pretty much it. They're not super complicated. They're just values that you pass in. And then the thing that's kind of new with ROS2 that you couldn't do in ROS1 is you can have a callback function on your node so that you can change those values while the node is running. And this offers you some really cool functionality. For example, if you guys are familiar with running proportional integral derivative loops, PID loops, you can make a node that is running a PID loop internally and then create a little GUI with some sliders on it and dynamically change the values for the P, I, and D while the node is running. And it lets you do that as part of an interconnected system that can send messages back and forth to everybody else. So it's a really cool prototyping platform to be able to do that kind of stuff on. Let's see. So let me just show you a quick code example of what some of those parameters might look like. So I want to kind of get a feel for how many people in here actually have like some coding background specifically in C++ or Python, to get an idea of like who to show this to. So how many of you have written some background applications in C++ kind of from scratch? Feel free to like either raise your hand or show it. Okay, so we've got me. Unfortunately, I have to stop sharing to actually be able to see people. Okay, so it looks like everybody in here has written some C++ applications. So I'll use the C++ example, and it's going to be one from within Autoware Auto. Give me just a second to find a good one. So the thing about Autoware that you'll find in a lot of cases is in Autoware Auto, everybody who helped contribute to Autoware Auto were pretty seasoned C++ and ROS developers. And so there are not that many applications within Autoware Auto that are like really simple applications. They're all either very complex and like obfuscated and hard to read, or they're probably not in Autoware Auto. So let's see. Let's use an example from Autoware Auto Create package. Actually, no, that doesn't have a parameter in it. Provider. Okay. Make this a little bigger so everybody can read it, and then share my screen again. Okay. So this is an example of some code that's in Autoware Auto. You'll always get the copyright up here from the Autoware Foundation, and then a handful of includes for other things you want to include. If you are passing messages back and forth, you have to tell your C++ application where to find the message definition that of the message you're passing. So that'll always be in a HPP file, and it will be under the name of the package that message belongs to. And then the MSG folder is where you store message definitions. So in this case, we're getting a message called HAD map bin, which is a binary representation of an automated driving map. So, and then you'll see some conversion utilities and so on in here. The part I was getting to is in the constructor of this node. So the node itself is named Lanelet2 map provider. Lanelet2, for those of you who haven't heard of it, is just a standard representation in the industry for a semantic map. So if you have an area and you want to represent lane edges and road signs, speed zones, construction zones, that sort of stuff, Lanelet2 is one of a handful of formats that the industry has chosen to use to represent those items. And so the purpose of this node is just to be able to read a file that contains all that data in Lanelet2 format, and then publish that file as a binary representation to a message that's on the ROS bus. So obviously the first thing this node needs is the actual path to the file that it needs to load. So this node declares a parameter of type string called map OSM file. Now, when you declare a parameter, under the hood, ROS uses some dynamic typing with C++ templates to be able to declare parameters of multiple different types. So in order to make sure that from that dynamic type, you are getting the actual string rather than like a double or an int or something, you have to call a get function and then pass it the type that you want to extract from that parameter. So this takes the map OSM file and then copies it into the map file name string. Now, what I said earlier is you can also hard code values into those parameters, and those are the initial values. The nice thing about ROS is that when you hard code those values, they're just the default values. So if someone passes in a different value for that, it will automatically override the value of the parameter with the same name. So for example, you have this parameter called origin offset lat and another one called origin offset long. And this is the offset of the latitude and longitude of the semantic map that you're loading relative to the other map that you're using for localization, something like a point cloud, where you're trying to localize your vehicle within it. And these are float 64s, also called doubles. And in this case, you're passing it a default value of 0.0. And you don't have to call the get function on this one, because passing in this default value lets the declare parameter function be able to deduce a type from the default value that you're giving it. So it understands that what you want out of this declare parameter call is a double. And then, as I said earlier, you get into a little bit more complex stuff in Autoware nodes, like checking to see if a parameter has been declared, checking to see if it has been overridden, those sorts of things. And then in this case, this makes Autoware auto nodes are always separated into the ROS portion and the pure core C++ portion. And the main reason for that is if we have to make any updates to it to support a new version of ROS, or you want to switch to another another middleware layer instead of ROS, you only have to change the wrapper portion rather than all of the core utilities and functionalities and algorithms that are in the core C++ code. So as an example of that here, the mmap provider variable is being created as a unique pointer to a class called Lanelet2 map provider, which is where all the core functionality for the Lanelet2 map provider lives.
Yeah, Josh, I was wondering if in the last half an hour or so you could go over the structure of Autoware. So then,
Yeah, I'd be happy to do that.
Yeah, because then they can start to look at specific parts of it before we talk again.
Yeah, absolutely.
And have more specific questions then.
Yep, that sounds like a good idea.
And also, is there a way for them to run it in simulator that they can then do after?
Yeah, so let's start with just going to, the main Autoware repository. So gitlab.com/Autoware Foundation, and I'll link this in the chat too, so you guys don't have to type all of it. There we go. So that is a link to the main GitLab repository. I recommend, if you have not created an account on GitLab before, that you do that sometime in the near future. You don't have to do it now. It'll take 4 or 5 minutes to get started because you have to verify some information, verify your email, etc. But this is where all of the most up-to-date code for Autoware Auto lives currently. The Autoware Foundation is actually in the process of migrating over to GitHub, probably I think for the 3rd time in their history, but they're moving back to GitHub and kind of restructuring Autoware. But for now, this is where you can go to get the most up-to-date Autoware Auto code. And then at the top of this page, you'll notice a link to the documentation. And I honestly think the documentation is pretty good, but it is definitely missing a few things. So what I would recommend starting out to get Autoware Auto and get it installed and running, go to the installation in the documentation. And then ADE is not really described very well here, but it's ADE stands for either the awesome development environment or the Autoware development environment, depending on who you're asking. And it is essentially a Docker-based environment that allows you to enter into Docker and attach some Docker volumes and get all of the dependencies pre-installed and all that stuff with just one command. So it really makes it a lot easier to work with if you don't already have Ubuntu 2004 with ROS2 with all the dependencies already installed on your machine. However, I recommended in the chat message that I sent before this class that everybody install Ubuntu 2004 natively and then install ROS2 natively on top of that. And the main reason for that is when you're dealing with autonomous vehicle environments, Docker is usually not recommended. You want to reduce as many layers and possible latency introduction as you can when you're dealing with like an on-vehicle environment. So generally you want to install straight on the hardware with no abstraction layers in between. So you'll want to do the installation without ADE for the instructions here. It has you go through the ROS2 core installation, which you guys have already done. So you can basically start from the section here that says once installed, dependencies can be deduced from the sources of the Autoware Auto project, and here's the commands that you'll want to start with. So this starts by cloning down a copy of Autoware Auto, and then install some repositories from GitLab and GitHub that are required to build Autoware Auto. And then it has you use a tool called ROS2, which I highly recommend looking into in the future. ROS2 is really nice for being able to automatically install all of the necessary dependencies for a stack of ROS tools. And then once you're done with the installation, I do not recommend doing this last command here, which checks out the 1.0.0 release. The 1.0 release was quite a while ago, like February of last year, and there have been huge improvements made to Autoware Auto since then. So I recommend just staying on the master branch that gets automatically cloned down. But then after installation, you can go to the building section on how to use the Colcon tool to build the environment and how to start messing around with Autoware Auto. And then finally, once you have Autoware Auto built, you can go to Installation SVL Simulator if you want to actually get up and running a simulation environment where you can run a vehicle and run a couple of examples that are in the Autoware Auto code. And those are all listed under usage, I believe. Yeah. So usage has general demos, autonomous valet parking demonstration, which was the demo we did at the 1.0 release, starting up the behavior planner, global planner, NDT, etc. And we'll talk about what each of those means here in just a second. Okay. So, actually, we're going to go through this one because it actually makes things a lot easier to talk about. There we go. So there are many more nodes in Autoware than I could ever talk about in a single hour and a half course. But the majority of those nodes that provide some useful functionality were used in the autonomous valet parking demonstration that was done by the Autoware Foundation last February. So I'm just going to use the architecture diagram that was written for autonomous valet parking to kind of describe autonomous systems in general, because a lot of these concepts crossed over to pretty much every autonomous vehicle you'll find, and then talk specifically about some ways that they were implemented in Autoware Auto. Okay, can you guys read that okay? All right. So in the autonomous valet parking demonstration, we were essentially using one vehicle with 2 LiDARs on top, and for localization and object detection, that was it. It was just about the simplest you can possibly get in terms of being able to navigate around and not hit anything by just using 2 LiDArs. So we had a front LiDAR and a rear LiDAR, and those each had their own ROS2 drivers, which would communicate directly with the hardware and bring that data into ROS2. Then start the Autoware nodes, like the point transformer. And the purpose of the points transformer is to be able to take all of those LiDAR points that are being generated by the sensor and move them into a common frame of reference so that all of the points are able to be fused together into a single point cloud. When you receive the data from each of the sensors, it's going to be in the sensor's reference frame. And ROS understands that and represents that with what's called a frame ID. So every message that you get from that ROS2 driver for the LiDAR is going to have a frame ID attached to it. And that needs to be unique on every sensor so that ROS can build a transform framework of how to get from one frame of reference to another. And really all this points transformer did is it would look up the frame ID that was being given by the LiDAR. It would look up the frame ID of the common reference frame that we wanted to merge everything into, and then it would just transform each of those points into the common reference frame. So each one of these would produce a point cloud that was transformed into that common reference frame, and then the point cloud fusion node would fuse all of those points into a single point cloud that could be used for localization and for object detection and avoidance. So from there, the fused point cloud would be fed into a voxel grid downsampler, which would just take a voxel grid of a defined size in the configuration parameters and downsample all of the points that are within that voxel to a single point. And depending on what voxel method, downsampling method you chose, it would be either the center or random sampling or so on. But it would basically make the point cloud significantly less dense, because from a 32-layer LiDAR, you're getting somewhere around 600,000 points a second. And downsampling each of those into something that is much easier to match with like an NDT matching algorithm is really important. So the point cloud would get downsampled and then be passed to the NDT localizer, which would use a nearest neighbor algorithm to try and match the current scan that was being taken with a pre-existing point cloud map. So you would go to the site, use the LiDARs to make a merged map of all the frames that it recorded over a period of time, and that is your reference map. And then the single scans that you're taking with the LiDAR real time can then be matched against that reference map to figure out where you are. In addition, the point cloud data that was fused would go through a ray ground filter, which would take each of the LiDAR rays and figure out at what angle they were being projected and how far they were going, whether there were any outliers, stuff like that, and then be able to dynamically figure out which of those points that were returned were ground points versus obstacle points that were out in the environment. And obviously, when you're driving around, you don't care too much about the ground as long as it doesn't have like massive shifts in variance. So the points from the ground were essentially thrown away in that profile. And then the points that were left would be run through a Euclidean cluster algorithm, which would group them into clusters that can be used for detection and avoidance, which is what the object collision estimator did. So to be able, that's how we figure out in the Autoware stack where we currently are and what objects are around us. But then in order to actually be able to drive somewhere, you have to have planners in place. So we had two planners that are part of the Autoware Auto stack, a global planner, which would say, this is my current ego vehicle position, and this is the position and orientation that I want to end up at. Now, using that semantic map that I've got a copy of, figure out which segments of the map connect to each other to create a path from the current point to the destination point. And that's the whole point of the global planner. It is just there to figure out which segments you need to traverse to get from point A to point B in the semantic map. But once you've done that, you have to have a little bit more fine-grained information to figure out how to actually actuate the vehicle to traverse each of those segments. So that's where the behavior planner comes in the Autoware stack. So this global route from the global planner, which consists of a set of segments, would be passed to the behavior planner. And then the behavior planner would look at each of those segments and call up the Lanelet 2 map loader and say, for each of these segments, give me back the segment type. And that segment type, in our case, since we were just doing really simple routes in a parking lot, would either be a lane segment or a parking segment. So the behavior planner would dynamically decide, based on the segment type, do I need to call the lane planner or the parking planner? And when it would call one of those subplanners, the purpose of that subplanner is to take the geometry of that subsection of the route and then create a set of waypoints that lies along, in the case of the lane planner, it just lies along a center line of the lane. In the case of the parking planner, it was a lot more complex. It would involve all of the surrounding edges of the nearby lane segments, plus any static obstacles we detected, plus any the desired orientation in the parking spot. And in the case of Autoware Auto, it would actually use a fourth order problem-solving algorithm to try and solve the equations necessary to create a route within those geometric boundaries. And for that reason, then the fact that we only had one person maintaining it who actually understood how the algorithms worked that parking planner has been dropped from Autoware Auto. So don't go looking for the parking planner in the code base. You won't find it anymore. It's being replaced. But the lane planner is actually a pretty good example of how to convert a high-level segment traversal into a set of waypoints that you can actually drive with a local controller. So once the behavior planner would receive this global route, it would parse every segment out, give them to the subplanners, and then get back a set of waypoints. And then it could conglomerate all those waypoints from the individual calls to the subplanners into a complete drivable route. And then it would pass that route as what we call a trajectory, or the next 100 meters or so of that route, to our MPC controller. MPC is just model predictive control. It's a pretty common algorithm that you can tune based on weights for whether you want the sticking to the path to be more important, or the orientation of the vehicle relative to the reference trajectory to be more important, or so on. It's a little bit more complex than like a pure pursuit algorithm, but it's a lot more accurate at maintaining the variables that you give high precedence. So that trajectory would get passed down to the MPC controller, and then the MPC controller would calculate the wheel orientation and the velocity that the vehicle needed to be at in order to try to meet the next set of waypoints in front of the vehicle. And it would pass the next, I think we did 10 seconds of driving controls to the vehicle interface within Autoware Auto. The vehicle interface is a generic API layer, so it doesn't really matter what kind of vehicle you're trying to control underneath the vehicle interface. The data that gets passed to the vehicle interface is just a set of like orientation and position values. And then the vehicle interface will translate that into specific wheel angles, specific velocities, specific like tread rotation velocities, depending on what type of vehicle was underneath it. It would translate those into vehicle-specific controls, and then that would get fed to a driver that talks to the drive-by-wire system at the very bottom layer. So every vehicle that you want to be able to control with Autoware Auto or with any ROS2-based system needs a ROS2 driver so that it understands how to take these ROS messages and turn them into, for example, CAN messages or Ethernet packets or whatever to talk to that drive-by-wire system at a very low level. And when we have the in-person course, I'll go through a little bit of how that works with the specific drive-by-wire system that'll be on that vehicle and how we'll get it talking to Autoware and hopefully be able to just drive a basic GPS-driven waypoint route with that vehicle. So I know I went over a lot of information there. Please feel free to ask any specific questions that are coming up in your minds, and I'll be happy to try my best to answer them.
So Josh, one question is, now that if they install Autoware Auto and even like say look at the code for this, what can they practically run as like, you know, a hello world in the LG simulator?
Sure. So the first one that I would recommend is just to get okay, so I have to mention a couple of things. One, the SVL simulator requires an NVIDIA GPU. So if you do not have an NVIDIA GPU on the machine that you're running, you won't be able to run the SVL simulator. However, in the examples that are in here under usage, if you go to the 3D perception stack demo, which is the first one that I recommend you run, there's a section here called generating sensor data, and it talks about how to use the simulator or how to replay sensor data from a PCAP file, which is just a network recording. So you can download this PCAP file, and then you can use a tool called UDP Replay, which you will have to install separately. It's installed in the ADE container, but it's not part of normal Ubuntu, so you'll have to install it separately. But you can replay that data and then run the Velodyne driver that we include in Autoware Auto to generate some LiDAR data without having to run the simulator. So I recommend starting with the 3D perception stack demonstration. If you get that one up and running, there's another one for doing a record replay planner demonstration, which is what we will also be using. Let's see. I believe this one might require. Yeah, unfortunately, this one also requires the simulator in order to be able to run, because the sensor data that was recorded in that PCAP won't match up with the environment that's in here. So we may have to set up like a, Rahul, is there like a shared resource that could be available to run the simulator?
Yeah, I mean, like we could run it on a standalone machine or on AWS also.
That's true. Okay, so yeah, the standalone machine is probably going to be better for that, because AWS by default, it's really hard to set up an environment where you can pass ROS data out of it.
Yeah.
But once we get the whole RoboMaker thing running with the F110th group, we might be able to offer that too.
Yeah, we can. So how you want to use a standalone machine for this one?
Yeah, if you have one available that's got an NVIDIA GPU, then it would be really helpful to have that available, at least for the in-person class.
Okay. So if we were to sort of plan another, so what do you want to plan, want to cover for the in-person class then, or for the next tutorial?
Sure. So for the in-person class, I think it'll be really helpful to use, to essentially have people make their own ROS node, and then go over setting up like launch files and configuration files for the Autoware nodes that you want to run, and getting information off the car about where the sensors are located and how to merge, how to set up the frames of reference in a URDF file, that sort of stuff.
Okay, and that might make more sense if there is a physical car, right? That is,
yes, definitely.
Yeah. Okay, so yeah, I think we'll figure that out in a few days.
Yeah, that sounds good.
Okay, guys. So is this like, I think we would do the demos, on our own after this, and when we sync up. And any other questions? Were you able to run everything?